So I'm just jumping in a little here to the calculation that has already been described in the previous video. What's interesting here is you can see a picture of the product it was based upon. And you can also see how we sit these machines on a pontoon. These things here these legs extend down onto the seabed to provide a more stable platform for the excavator to work on. But you can see here where all the calculations are, and we can see the controls here if I will lift the arm up a little bit. And let me just see what's going on there. Oh, there we go, sorry, okay. I wasn't quite sure what was happening. So I'm activating the boom there. There's the boom, and then there's the next ram is controlled by this one here. There we go. Or maybe it's easier to see it moving down. There you go. So we're moving each of the rams into their own particular position. And as that happens, all the calculations update in a live manner. You can see down here there's a lot of additional calculations, some calculations here for cylinder forces and some calculations here for fatigue loading. What I want to do now is to kind of step away from the calculation and go into the approach that we're using. So the first part of designing this job was to write a structural specification. So if I go up to the summary here, what we're doing, maybe I could point you to the map. We start by looking at our key assumptions, and then we have a number of criteria to work with. So there's proof load cases, we've got safety load cases, fatigue load cases, and the proof load cases are defined here, and some safety load cases defined here, and the fatigue load cases are defined here. So if we just run through this very quickly, maybe look at the key assumptions first of all. So there are some assumptions here about stability limits and toppling of the vehicle. Some other assumptions here about wind loads. So that's just setting out normal assumptions. Let's just jump into the proof load cases. So this is one of the configurations of the machine that gives me a proof load case, and it's called the bucket ram breakout force, and it's when the bucket is arranged so that we can achieve the maximum load on the tooth of the bucket. So the distance between the pivot point and the ram is maximized. And that is. Otherwise, what would happen is, as you increase this force, you would get this ram would vent off from its relief valve setting, and it would not be able to sustain such a force. So this is the geometry in which we maximize the amount of load we can put on the tooth of that bucket. This is kind of critical to the design of these types of machines. And at the same point, at this same configuration, we also get the dipper breakout load. So this is the case for the this arm here, but the dipper arm is also very highly loaded in there in the same situation. This is a swing load case, so it's obviously just swinging around from one position to the next. And we've got some safety load cases here. So there's some safe working loads that you have to work to. So each machine will have its safe working loads, and they have to be limited to 87% of the hydronic limit, and that's set by some automotive specification there. The fatigue load case is really what I want to have a look at here, because it's fatigue that we want to concentrate on. And what we've done is we've invented what the machine's going to do, a load cycle, if you like. So this is the machine, and it's stretching out to pick up a piece of rock armour. So here it's picked the piece of rock armour in the same position. So we look at that as one load case. Then it goes to this load case with a heavy weight hanging from the end of it. Then it's kind of lifted up and lowered into position, and then it extends out, and then they drop the load. So That's the load cycle that we're considering, and we've generated this this will operate for 7 hours per day for 200 days per year, and so that's 42,000 load cycles. And we've also split that into movement of 6-ton rock armour, half of the cycles, and the other half of the cycles it's moving 3-ton of 3-ton weight of rock armour. So there's that's the kind of fatigue cycles that we're looking through. So when I come to do the analysis, which I think I've got in another document here, this one here, I'll go back to the top of this document here. Again, we first of all refer to the structural performance specification, which is the document I've just been through. And we've got a number of different approaches here. So obviously, in terms of working out the worst loading, my 2D model, just using Excel, has actually told me an awful lot about the worst configurations for those machines. And I use a lot of the kind of goal finding tools to maximize the offset moments of forces and things like that. So you can drive the calculation to work out the critical load cases using that little 2D spreadsheet model. But then I have what I do then is I take the geometry that I've calculated in the Excel model, and I build a finite element model to mirror or to match the configuration that my spreadsheet is in. So let's just have a look at that. So so these are taken from the structural specification, and these are this is the configuration we've got for them. The maximum the bucket breakout force here. Now this is a 2D model. It's not the 3D model just yet, because this is a symmetric load case, so I only need a 2D model. And what I've done is I've got a number of models here in ANSYS, and I've got some scripts where I can move and rotate these arms into position and connect them all together with pins, basically. So I reconstruct the geometry of this configuration, and that's shown here. And in there, I can put a horizontal and a vertical load, which puts a resultant force in that direction there. So from that, I can look at each of the individual arms and have a look at the stresses within the structure. So these are for proof load cases, but I can also use these same things to work out fatigue life. So you can see here I've got an SN curve. So I'm using this. So the first boom stress for breakout gives a digging fatigue life estimate of 14.1 years, which is actually pretty good, I think, for a machine that size. Generally, these types of machines are designed to have a very arduous service for 2 years. So that's actually a pretty good result for the machine. Here we've got some another part of the structure. So we're looking at how many load cycles we can get here. This is slightly less. This is only lasting 11.2 years. So, and we've got another part of the structure here which is lasting for 4.2 years. So the different parts of the structure are going to last different lengths of time, really. So that's following on here. Now we're looking now at the lifting assessment. So this is how much load can we carry at extended reach, and again we can kind of we use our ANSYS model to take this geometry and we build that geometry in our. Remember, it's just a symmetric model at the moment. And we can do our calculations based on this part of the structure. And again, as we go along, we're always keeping an eye on the fatigue life that we're going to get for these particular load cases. So then we go into these are the proof load cases. So what we're doing here is not working out fatigue life, we're actually working out the maximum stress in the structure, and we're looking for a reserve against the yield stress. So Now, for some of these load cases, see here I've got the load to be even more onerous. I've put the bucket breakout course not along the whole surface there, but I put it on the corner of the bucket. And this is maximizing so I'm getting some twisting of that arm at the same time. So, I need to use a 3D model to do that. So I've copied the model over, so the analysis is slightly bigger now. And again, we can look in detail at each of the arms there. This is the swing load case, which again, I've used, I think you can see here how there's a lateral force here. That's an inertial force from swinging and braking to stop the swing. So that's modelling that part of that particular load case. Then we've got some lifting load cases where we're looking at, we've got an allowable stress here. We're taking the yield stress times 0.575, and that becomes the allowable stress. So we can, here we go, we're stretching out reaching out as far as possible, hanging a load on here, and looking at the stresses that we get. And the 202 here, anything that's red is above that allowable. Now we can always manage, in the proof load case, we can manage with some small areas of very high stress. We can cope with that because we know that the material is plastic, and these like local areas of overstress would redistribute themselves across the section and would result in no discernible permanent deformation. So I'm not worried about small areas. If the whole section across here, which is currently shown in green, if that was all red, that's the time to worry when we're looking at red across the whole section. This is the fatigue load cases. So this is the rock armour placement. So here we are. Remember, we had a number of. We call this load case 1 for fatigue. So that's hovering above the load. That's picking the load up. That's load case 2. Load case 3 is moving it into position. And then lowering it down through the water is load case 4. And then a move to the drop position is load case 5. And release from that position and return to position 1. So it's going through that load case 1, 2, 3, 4, 5, 6. And we're going to repeat that for these numbers of cycles. Half of them for a 3-ton rock armour and half of them for a 6-ton rock armour placement. So we can see some familiar charts, so hopefully becoming more familiar to us now. So I'm doing some discussion of the worst fatigue details on the structure. And this is the load diagram here. This is load case 1. Let's start that. It's shown slightly unusually, but I'll tell you why. We're actually moving from load case 1, which is that point there, to load case 2, to load case 3 is here somewhere, load case 4, load case 5, and then load case 6 I've actually drawn here. So sorry, I've drawn load case 6 there. The reason I've done that is when we come to look at this a reservoir method for working out an equivalent stress range, what we do is we draw out this path that repeats itself. So this is a repeating cycle, and we pretend to fill it with water. So if you imagine this is full of water and this is full of water, then we drain from the lowest point. So if I drain from here, we're going to get a stress range that is equivalent to 2 stress ranges. So I'm going to empty that one. If that's how we imagine it, that gives us a stress range of load case 5 minus the stress from load case 4. So that's 1 fatigue stress range. And the damage from that will be added to the stress range from load case 2 minus load case 1. And that will be the second stress range. So, and for other parts of the structure, we get a slightly different result as well. So it really depends on which part of the structure is. But by looking at how the stresses change across the structure, that's how we work out what the equivalent damage is going to be made from the summation of a number of load cases, the damage from a number of load cases. And ultimately, all the calculations are done in a spreadsheet, we take the assumption that we've got a Class F structure all over. We assume that Class F structure exists all over the structure. So where that's a great simplification to make. If you know that you've always got better than a Class F weld, and you do your assessment, the whole structure to Class F weld, you don't have the complications that I had with, say, the bogey fatigue assessment, where we had to say different parts of the structure had different fatigue classifications. That's a lot more detail. But we're working out all the calculations here, and the results show that the minimum life prediction is 41 years, which is greatly in excess of the required 2 years. So we're all pretty happy with that. And here I'm actually taking those damage values that I've calculated from the spreadsheet, and I'm plotting them on the model. So this is fatigue damage at the critical location in the first boom top flange. So that's one critical location for fatigue. And we've got some more positions here. In fact, many of the locations were, because they're white, they've passed the assessment altogether. So it's limited to certain places. So overall, we're pretty happy with the design, and I think I've just got a few photos now. This was the arm being manufactured in Singapore. The machine was actually being worked in Perth, in the harbour in Perth. But what we've got here, this just shows the size of the structure, really. It is a big machine, and very good fun to be part of the design team here. So this is the machine being constructed, and this machine will end up on the back of one of those pontoons. This is showing you all the kind of the hydraulics are all here, and these cleats are probably welded on. It reminds me of the first fatigue job that I did, which was a nuclear fast wagon. And we spent a lot of time carefully considering the welds and the weld configurations. And I walked out into the workshop, and I saw that people were welding these hydraulic. It was a railway structure, but it had some. It was pneumatic systems for braking, and they were welding cleats on to my structure, my beautiful, carefully designed structure. They were just tacking on fatigue critical details all over my beautiful structure. I had to get them all taken off before the thing went out into service, but that was my first horror story, and probably not my last. Okay, thanks for listening.